Welcome. In this video we're going to talk through some ways to determine the heat of reaction, and we're going to be focusing on using heats of formation and using Hess's law. But first we're going to do an overview of the 4 different ways to determine heats of reaction, because you want to think about what the problem's giving you and which would be applicable in a given situation. So the first one we did in class is using calorimetry, and this is based on experimental data. And the type of data you want to be looking for is if the question gives you some information about temperature and mass, or you might be given a volume and density of a solution or a liquid, then that's a kind of scenario where you could be using calorimetry. You would also have to be given the value of C, which is the specific heat capacity for a solution. And then the second method, you would use this if you are given bond energies, or sometimes they're referred to as bond enthalpies. And you'll notice the bond energies, you'll be given them in a table. It might look a little bit like this. The bond energies are always positive. That represents the energy required to break apart a bond. And so the way to find the delta H based on bond energies is you take the energy required to break bonds and subtract from that the energy that's released from forming new bonds. So basically what it ends up being is you add up your reactant bond energies and subtract from that the product bond energies. So the really big takeaway with this concept is that breaking bonds takes energy and forming bonds releases energy. That's the big idea here. You'll notice that for type 1, Q equals mc delta T, this equation is on your equation sheet. For the second type, the bond energies, there is no equation on your equation sheet for this one, and that's again because they want you to understand that breaking bonds takes energy, whereas making bonds releases energy. Then we look at option number 3. This you'd use if you're given heats of formation. The symbol for heat of formation is delta H sub F. It looks like this. So you might be given a table with some delta H sub F values. The symbol might be given, or it might be written out as heats of formation or enthalpy of formation. And you'll notice with these ones, unlike bond energies, the heats of formation can either be positive or negative. And for the heats of formation, there is an equation that you find on your equation sheet, looks like this. So for heats of formation, it's the sum of the heats of formation for the products minus the sum of the heats of formation for the reactants. Notice that's opposite than what we do for bond energies. And then using Hess's law, there's no equation for Hess's law. The idea behind Hess's law is just that if you can add up 2 reactions or 3 to get another reaction, then the sum of the delta H's of those reactions will equal the delta H for the overall reaction. So we have this concept of adding reactions together to get a new and different reaction. And if you add their delta H's together, it will give you the delta H for the new reaction. Again, no equation for that one. Textbook references, highly recommend reading through these sections in the textbook, going through the sample problems in the book. So again, we're going to focus on the second 2 methods, the heats of formation and Hess's law. So first we're going to look at heats of formation and think about how it's different from a bond energy. So the heat of formation is the change in energy or enthalpy when 1 mole of the compound is made from its elements in their standard states. And we'll notice that the heat of formation for a pure element that's already in its standard state is going to be 0. So here's an example of what a heat of formation would look like for methane gas. So this is methane gas. You'd start out by writing, 1 CH4 as the product, and the heat of formation represents the reaction where you form CH4 from its elements in their standard state. So carbon is in the form of solid carbon in its standard state. Hydrogen is in the form of hydrogen gas, which is diatomic, H2. So you need 2 hydrogens to make CH4. So that's that reaction. Now let's take a look at what that would look like for calcium oxide. So if someone tells you the heat of formation for calcium oxide is negative 634.9 kilojoules per mole, well, what reaction is that representing? Well, it's the energy to make 1 mole of solid calcium oxide. I'm going to put a 1 there. We don't usually write the 1, but I'll leave it. And it's making it from its elements in their standard state. So calcium oxide is made of calcium, and calcium metal is a solid at room temperature. That's its standard state. and it's also made from oxygen. Oxygen is a gas at room temperature, and oxygen is diatomic. So that's what oxygen looks like in its standard state. And then I have to work out the stoichiometry to make this balance out. So I have 1 calcium on the left, so I need 1 calcium on the right. And over here on the right, I've got 1 oxygen. Over here, I've got 2 oxygens. So normally we would change the coefficient on the right to a 2, but because of the way this is defined, the heat of formation is the energy to make 1 mole of the compound. So I cannot change this coefficient. So what I'm going to have to do is actually use a fraction. So that's why you sometimes will see fractions showing up in these equations, which might seem weird. It has to do with the definition of the heat of formation. So to make 1 mole of calcium oxide, I need half of an oxygen molecule. And when we say that, so when we talk about this delta H value, it represents the energy, in this case, that is released during this reaction. And we know that if the coefficients change, the delta H would change. So the coefficients are important to pay attention to. Okay. So again, heats of formation, if you have a heat of formation problem, you're going to be given a table with the relevant delta H values needed for the problem. In the practice problems in class, we're looking at a big table with lots of values in it. If you're looking at a test or the AP test, they would give you a smaller table that just had the relevant heats of formation on it. You might be given a few that are distractors that maybe you don't need. Something else you will notice is you will probably not be given the delta H values for elements in their standard states, because you're expected to know that the delta H for those is 0. Because if you think of the definition, like let's look at an example right here, chlorine gas. The delta H sub F, so the heat of formation for chlorine gas, is the energy required to make 1 mole of chlorine gas from its element in its standard states. So what's chlorine made of? It's made of chlorine, and chlorine in its standard state is Cl2 gas. So what's the delta H for this reaction? It's 0, because it doesn't take any energy to turn chlorine gas into chlorine gas. It's already chlorine gas. So you will be expected to know that. And if you look on your equation sheet, this is what the equation section looks like. So we've already used the calorimetry equation, and right now we're looking at this equation right here. It's the third one down. So for heats of formation, it's the sum of the products minus the sum of the reactants. We'll talk about those other 2 equations later. So looking at a homework problem, these are from page 8. And this question says, using the heats of formation, find the delta H for the formation of carbon dioxide from graphite and oxygen gas. So my equation, it's going to be the sum of the delta H of the products minus the reactants. And again, remember, this one is not one you have to memorize. It is given on your equation sheet, so it's products minus reactants. So who are my products? It's CO2 gas. I've already highlighted it for us here, so it's negative 393.5. It is important to pay attention to states of matter, because like liquid CO2 and gaseous CO2 would have different delta H values. So this is kilojoules per mole. And then my reactants are graphite, okay, and oxygen. And notice those are highlighted here in blue. Those have delta H values of 0 because they are already the elements in their standard state. So the answer to this one is just negative 395. Sorry, negative 393.5. Okay. Looking at this problem, we're trying to find the delta H for this reaction right here. It says, if you read the problem, it says, calculate the heat of combustion for 1 mole of methanol. And that's just describing this reaction right here. I can see it's a combustion reaction because I have a hydrocarbon reacting with oxygen. It's making CO2 and water. And notice that the coefficient in front of the methanol, so this right here is methanol, the coefficient is 1. So this reaction represents the combustion of 1 mole of methanol. That's what they're saying. So again, I'm going to find the delta H, I'm going to take my products minus my reactants. And my products are CO2 gas, which is negative 393.5. And again, you look at this table, it's in your textbook, it is also in OneNote. My other product is liquid water. Important to pay attention to the state of matter because gaseous water and liquid water have different delta H values. So liquid water is negative 285.9. 2.83. And then I'm going to subtract from that the reactants. So methanol gas is negative 201.2. And then oxygen is not, well, actually it is right here. But a lot of times you wouldn't be given the value for something like oxygen because you're expected to recognize that it is an element in its standard state. So you would take 1.5 times 0, which is just, 0. So you've got, if we plug this in our calculator, so 285.83 times 2 plus 393.5. It looks like you've got negative 965.16 is the sum of the delta H's for your products. And if you subtract from that the reactants, so you're subtracting a negative, so that turns into a positive. So make sure you're just being careful with sign, because sign really matters in thermo, okay? So it should end up being negative 763 if I did my calculations correctly there. All right, so that was it for heats of formation. Now let's talk about Hess's law. So again, Hess's law, there's no equation here, it's just a concept. The idea that if an equation can be expressed as the sum of a series of steps, the delta H for the overall reaction is the sum of the delta H values for each step. So if you look at this example, let's name these: reaction 1, reaction 2, reaction 3. So notice how you can think of reaction 3 as being the sum of reactions 1 and 2. And if that's true, then the delta H for reaction 3 will be the sum of the delta H's of reactions 1 and 2. So we see this idea of adding together reactions to get a new reaction. We see that pop up in redox balancing, where you're adding up, where you're balancing a redox reaction by the method of half reactions. We see this in kinetics, when you look at the overall reaction as being a sum of a series of steps. So this is just another kind of application of this idea. And it's important to know going into this two relationships involving the delta H for a given reaction. So one of them we've kind of seen a little bit before, this idea that the delta H value depends on the coefficients. So you can see right here, and this is an excerpt from your textbook, that for example, if you double the coefficients, it would double the delta H. If you triple the coefficients, it would triple the delta H. If you cut everything in half, it would cut the delta H in half. So there's a relationship between the coefficients and the delta H value given. So that is one example. And then the second kind of rule to know is that if you flip a reaction around, the delta H will flip in sign. So in this example, going from A and 2B to C is delta H1. If you flip that reaction around, the delta H becomes negative. So we'll look at some examples of what this means in real life. But let's put some numbers by it just to make sense of this. So in this case, if the delta H here was positive 10, if you flip the reaction around, the delta H would be negative 10. And then over here with this first one, if this one had a delta H of 20, if you doubled all the coefficients, then the delta H would become 40. So that's the idea there. So with Hess's law, it's kind of like a puzzle. You're trying to see how can these given reactions fit together to make the reaction that I want. So the way that you'll know it's a Hess's law problem is, notice how I'm not given temperature information, so I can't do calorimetry. I'm not given bond energies. I'm not given heats of formation. What I am given is some delta H values for some reactions, and I'm asked to find the delta H of a different reaction. So if I see a problem like this, I'm going to know that, hey, this is a Hess's law problem, and I have to figure out how I can add together these two reactions to make my overall reaction. So what I like to do is I like to look at my kind of goal here. There we go. And I want to somehow add these two reactions together, and in the process I might multiply by a coefficient, I might flip them around, but I want to somehow add these two together to make it look like this reaction right up here. So I'm going to focus in on, you want to pick a particular reactant or product to focus in on. So right now what I'm going to look at, what's catching my eye, is the fact that there are 3 CO2s on the product side of my reaction. So I'm going to look through these two reactions that I'm given and say which of these have CO2 in them. Well, it looks like this first reaction has some CO2 in it, but it only has 1 CO2. I want 3 CO2s. So what I'm going to do is I'm going to multiply this whole reaction by 3. I'm going to rewrite this down here. So it's 3 carbons and 3 oxygens make 3 CO2. And when I multiply that by 3, my delta H also has to be multiplied by 3. So it's going to look like this. Now I'm going to focus in on something else. How about this? It looks like I also make 4 irons. So I want to look through and say which reaction has iron in it. Well, it looks like this reaction has iron. But notice this reaction has iron as a reactant. I want iron to be a product. So I'm going to flip this reaction around. So 4 Fe2O3 makes 8 Fe and 6 O2. And when I flip a reaction around, it changes the sign. So instead of negative 3,296, it becomes positive. Okay, so now I've got the iron on the right side, but notice I actually want 4 irons. This one has 8 irons. So I'm going to multiply all this by 1/2. So I have to multiply this by 1/2 as well. So if I do that, I'm going to write that underneath. That gives me 2 iron oxides and 4 irons and 3 oxygens. And then my delta H now is 1/2 of 3,296.8, which is positive 1648.4. I'm going to kind of scribble this one out in the middle if that's okay, so we can know to ignore that. Cool. And now I'm going to try and add them together and see if they will give me my overall reaction. And if not, I can go back and reassess and see if I need to fix anything. One thing that stands out is notice how I've got 3 oxygens on the left and 3 oxygens on the right, so they cancel out. It looks like nothing else cancels. So I end up with 3 carbons and 2 iron oxides on the left and 3 CO2s and 4 irons on the right, and looks like that is exactly what I was hoping for. Hooray! I have managed to rearrange my 2 given equations and add them together to get this overall reaction that I was aiming for. And then the delta H of this reaction is going to be 1648.4 plus, let's see, 3 times 393.5 plus negative that, so 1648.4. So it looks like you should be getting positive 467.9 kilojoules. This is the type of problem you're probably not going to be graded for sig figs on, so I wouldn't worry about that. Of these 4 problem types, you're most likely to be graded for sig figs on calorimetry, because that is the one dealing with real experimental data you might collect in a lab, like go collect mass and temperature data. That's just an FYI. Okay, so again, if you add these 2 reactions up to get this overall reaction, you can add up their delta H's to get the overall delta H. So now let's look at another one. This is the reaction we are aiming for. I want 1 gaseous water on the right and 1 liquid water on the left. Okay, so I'm going to take a look. I'm going to focus on this first. I want 1 gaseous water on the right. It looks like this equation has gaseous water in it, except this one is making 2 waters and I only want 1 water. So I'm going to cut everything in half. So I'm going to take 1/2 of this equation. So that would be 1/2 CH4 and then 1 oxygen and 1/2 CO2 and then 1 water. And then I'm going to take 1/2 of the negative 802, so that's going to be negative 401. And notice how I kept it going the same direction because the gaseous water's on the right, that's where I want it to be. And then I want liquid water to be on the left. So it looks like the first reaction has liquid water. It looks like I need to flip it around and multiply it by 1/2. Okay, so I'm going to flip it around and then I'm going to multiply it by 1/2. So I'm going to end up with 1, I should label these here with states of matter. Okay, I'm going to end up with 1 liquid water on the left and 1/2 CO2 and then 1 oxygen and then 1/2 CH4. And what I did here is I multiply it by 1/2 and I flipped it around so the sign flipped, so it's positive 890 instead of negative. And so I end up having, what is that, positive 445 kilojoules. Okay, and I want to make sure that these add up to give me the overall reaction I was looking for. So it looks like your methane cancels, your oxygen cancels, your CO2 cancels. So what you're left with is liquid water turning into gaseous water. So that is just liquid water evaporating. That's what we found the delta H for. And the delta H for that is we add up these two delta H's, so negative 401 and positive 445. We end up with about, what, 44 kilojoules per mole. So it takes about 44 kilojoules of energy to evaporate 1 mole of liquid water. All right, so hopefully that helps. Thanks for watching. Let me know if you have any questions.